Hello everyone and welcome to the 23rd lecture of the course Advanced Structural Analysis. We have briefly discussed the method of the generalized stiffness. Before that we also discussed the method of the generalized flexibility, and these methods were based upon the standard or the simple flexibility in the matrix concept, which we take up from the standard force and the displacement method. Now, to conclude the overall discussions which we have done up to now in the course, we will try to see one simple problem which is based upon a partially restrained system and try to solve it using all these set of approaches which we have typically seen up to now, and we will try to see that what are the major differences which exist between the different methods, and this will give us a motivation now to bring down the method which is based upon the computer implementation of the given system. So, this is the problem which we will be trying to discuss in this case, a problem with the partial restraint, and the solution we will be trying to extend with the simple flexibility and the generalized flexibility approach. In the subsequent lectures, we will also move it with the similar problem and the methods of the stiffness in the given system. To start with the problem statement, we have considered a simple beam which is subjected to a UDL at one of the span, and the second span is subjected to a condition of the support which is partially restrained. When we mean by the partially restrained, that the system is not fully restricted to move in the vertical direction. There is a spring which is attached to it which has its own flexibility identified, and due to this flexibility of the spring there will be a partial movement which will take place at the given system. Now, as we have already discussed the standard flexibility approach both for the simple and the generalized cases, we will try to see this problem in a bit brief. I will show all these steps, but it is also expected that while we discuss the problem, later on all the learners should see the problem once again with all the subsequent steps and try to do those calculations on their own to verify that whether all the values which we are trying to show in the subsequent steps are familiarly obtained or not. So, to start with, a simple flexibility approach or a direct flexibility approach, which is the name given at times, will be used. We considered that in this method we identify the redundants of the given problem, and the post processing typically requires extra steps which makes the method not very much suitable for the generalization to the large scale systems. Another issue which appears with this method is that there is not a unique system which we can define with respect to the statically determinate problem which we will identify, and this remains one of the reason why the simple flexibility approach cannot be extended to the computer systems, but still we will try to just see the briefly a problem based upon it. So, these are the brief steps which we typically follow to evaluate the response of the given system. We define the degree of static indeterminacy first, we identify the redundant and we convert the given system into a stable statically determinate system, and of course, we must note that this is not a unique step. Based upon different users, this can have the different set of systems and all be possible. Then we also break down the system into the system which is subjected to the external loads only, a determinate system as has been defined in the step 2, and a system which is subjected to all the redundant loads one by one in the given process. We consider the redundants as an external load of the given problem, and now we try to evaluate the conditions of the deformations which are occurring due to the external load system as well as the deformations which are occurring due to the redundant force system, and that is called as the flexibility coefficients of the given problem. And once we have all these parameters available to us, we define the generalized compatibility conditions in the direction of the given redundants, and that is evaluated for the unknown calculations which are the unknown values of the redundants in the given problem. Once we have the values of the redundant available to us, we go ahead with the calculations of the remaining support reactions and the internal forces by the post processing steps. So, as a simple procedure, as a step 1, we identify that the given problem has 3 number of reactions. It is an open system, so internally it is determinate. For external system, we can evaluate that it is having an indeterminacy of degree 1. While doing it, we have considered that axial deformations are not possible. That means, I am only considering the vertical translation and the rotations of the given system. There are axial deformations which are not permitted. That means, the members cannot actually change their length of the given system. Now, based upon this given system, as a step 2, we need to identify one redundant of the given problem, so that we can convert this given statically indeterminate problem to a statically determinate problem of the given system. As a simplified procedure, we have considered that R3, which is the reaction in the direction of the spring component is one of the redundant of the given system, and this we have identified as the A of r, or which is the redundant of the given system. So, once I remove this part of the reaction, the remaining system becomes my statically determinate system, and on the same system, removing the load, I bring the calculations of the A of r or the redundant value, and that becomes my redundant system of the given problem. So, important thing to note is that for both of these systems which we have identified, we have the degree of static indeterminacy which is 0, which means I can solve these two systems by the simplified procedures which are known to us. Only thing is the A of r is a unknown parameters. So, now we will try to evaluate the response of the system or the displacements and fit the condition of the compatibility to know the value of this unknown parameter A of r. As we go ahead with the step 4, we calculate the deformation due to the external load system as well as the flexibility coefficients for the redundant system which has been identified. To calculate the deformation due to the external load system, now this is the external load system which we have defined. With respect to this system, if I want to evaluate the deformation over here, and the deformation will also be evaluated in the direction of the redundant of the given problem. So, that is why we are looking to evaluate the displacement at the given position. Now, this deformation, to evaluate it, we will just bring up one virtual system as well. Now, bringing the virtual system even in the problems where you already have a load active at the given system helps us to evaluate the flexibility coefficients also of the given problem, because we realize that at a later point I need to also bring this unit load to calculate the flexibility coefficients. So, we can consider that this is the real system with which we are evaluating the deformation at the given point, and to evaluate this displacement we are taking help of a virtual system in which we have applied a unit load in the direction of the required displacement of the given system. And while doing the virtual system, I will also be able to identify the flexibility coefficient of the given problem. We will now evaluate the moment distribution in the given beam. So, we have considered the section from right to left, in which we are considering any position which is x distance away from the right side. At this, the moment can be described. So, W into L into the given value of x. So, this is the amount of the moment which has been described. Now, important point which we have already discussed earlier, that the sign conventions which we typically follow in the course, they are identified in this manner, being positive, and the moments in the opposite direction have been considered to be negative. One important aspect one can always remember, that sign conventions are the human made. So, it is not a concept which are strongly suggested to always follow in the similar manner. If you follow one particular sign convention, it is very well, because one can always get the results without having much confusion. But even if one goes with a different sign convention and does not follow one specific one, in a given set of problem one should consistently follow a standard convention, and that will still solve the problem with the same ease. So, while doing this problem, even if I go with considering these moments being positive and maintain that throughout the given problem, still the solutions can be obtained. But just to avoid any further confusions, we will consider that these sign conventions are considered to be positive, whereas these amount of the moments have been considered to be negative in the given system. So, with this point in mind, we understand that between the span B to C, the moment distribution can be described by this expression, whereas once you move to the given span over here, somewhere at this position, the distribution of the moment will now also be affected by the reaction load which is appearing from the support at B and the uniformly distributed load of the given system, and that has also been identified over here. We have identified these support reactions by solving a simple statically determinate problem first, and that is why the W5 WL upon 2 or WL upon 2, these are the set of reactions which are known to the user by solving the determinate system of the given problem. In the same manner, for the virtual system also one can evaluate the amount of the moments in the given problem. As we have considered the moment in the positive direction of the displacement, which we have considered to be unknown for the given problem. So, we have considered this value as 1 unit, which is in the positive direction of the redundant A of r, and with this point in mind, we evaluate that the moment at any given position x distance away will be positive x, and section which is over here, it will be evaluated with 2L minus x in the given problem. Now, once we have the moment expressions of the given system, we can now evaluate the amount of the displacements in the direction of the given load, which is the delta L component. We can also evaluate the flexibility coefficient of the given system, and using these two parameters of the given system, now we can specify the condition of the compatibility in the given problem. what we realize that the compatibility condition can be described by this standard form, where delta is the compatibility parameter or the effective displacement at the given point where the redundant has been considered. Delta L is the deformation due to the external load in the position or in the direction of the redundant. F is the flexibility coefficient, which is corresponding to the given redundant positions of the given system. Right now we have only one redundant value, so that is why the flexibility coefficient happens to be only a single value, which is f of 1 for the case. Now only issue out of the delta L and F which we have evaluated is now to know the value of delta, which is the compatibility condition of the given system. But we realize that if there would be a solid support here which is completely restraining the movement at this position, the delta value would become 0, because that will not allow any of the movement to take place at the position of the support C. But as the support C is subjected to a spring support, it will also undergo some amount of deformation, and to know that amount of deformation in the given system, we must consider now that the deformation will be corresponding to the identified flexibility of the given spring member. And for that, if I consider that in the given system over here, if the force which is being considered as the redundant value A of r, the equal and opposite force will also be transferring to the spring system in the given problem, and this will make it that the spring will move downward, which will generate the reaction of A of r or the redundant value of A of r in this given member. So, to consider this part, we include over here the amount of the deformation due to the spring component, and that is included as the flexibility of the spring into A of r, which is the force in the spring component. We must again repeat this component, that as we are considering the spring to be over here, the amount of the force which we are considering as the redundant, the same equal and opposite value will be translated to the spring component, and that is why the force of A of r is being considered to be active in this spring. It is being multiplied with the flexibility of the given spring, and that will give us the net displacement of the given system. The direction of this force is downward, and that is why we have considered this overall value with the negative sign, considering that the positive displacement or the positive direction of the redundant is considered upward in the given problem. With these 3 points in mind, we have now included the value of delta L, the flexibility coefficient f of 1 as well as the compatibility parameter delta of the given system. Once we substitute these in the given process, we can evaluate the standard result, which is the unknown value of the redundant of the given system, and that comes out as 5/8 WL in the given problem. The value comes out to be positive, which means that it is the vertical reaction which is appearing at the point where the spring is supported. Now, as a step 6, we also move ahead with the post processing of the system to evaluate the remaining set of reactions in the given problem. To evaluate the remaining set of reactions in the system, we go back to the same original problem, where we have considered that these are the two systems which we initially considered, the determinate systems, one which is subjected to the external load. So, this is fully known to us, we have a determinate system with every external load known to us. The second system, which was a determinate system with the redundant value, has now been evaluated correctly, because we have evaluated the redundant value in the given system. And now, with this point in mind, we can consider that the net reaction forces of the system can be evaluated, and those system forces can now be looked into this particular manner. So, once we identify these system reaction forces, we realize that the system of forces which are considered with respect to the reaction R1, R2 of the given system, they can be identified. At the same time, the internal member forces which are being called as A of M1, A of M2, that they can also be identified. A of M3 and A of M4, which are the member forces in the member 2, they can also be identified. And finally, the member force which is appearing in the spring, that can also be identified in the given system. So, what we will do, we will try to correlate this particular diagram in which we have identified all the requisite set of forces which we require with the set of overall system which we have generated over here. So, as we do this, we realize that R1 and R2 are these two values which are appearing in the given system, WL/8 and 5 WL/4, and similarly the member forces can also be evaluated. The values have been identified with respect to the sign convention which has been defined in this diagram. So, accordingly the values have been considered with respect to their respective values over here, as these values appear as the reaction R1 and R2, both are in the positive direction of the reaction. So, they have been positive. Similarly, over here we can consider the set of forces, and they will become the AM1 to AM4 in the given process, and this is the AM5 which is downward in the given system. As per the sign convention, we have AM5 upward positive. So, we have considered the value of minus of 5 WL upon 8 in the given problem. So, one can just see these values, try to correlate them with respect to the overall calculation or the steps which we have shown, so that the overall steps can be effectively understood in the given process. Now, once we have identified the given system, we again extend the same problem, and we now try to extend it with respect to the generalized flexibility approach. As we have said that the standard process of the flexibility which we just did will not give us the evaluation of all the unknown parameters of the given system, that means the displacements which are at the respective nodes or the set of reactions of the given system. We have to do a post processing in the given system. To reduce that effort or to make it more systematic, we come up with the element based flexibility matrix or the method, and that is what we call as the generalized flexibility approach in the given system. So, now the same problem we will try to adopt with respect to the generalized flexibility. As we understand, this method will overcome the problems of the post processing. Typically, as we have a structured approach to evaluate the response of the given system, so we will not only evaluate the unknown redundants of the given problem, but we will also be evaluating the reactions of the system in the process. We will also be knowing the unknown displacements which are occurring in the given problem, and that makes it much more easier rather than doing the post processing of the the actual flexibility matrix of the given system. These are the brief steps which we have earlier also discussed, that we define the degree of static indeterminacy of the given problem, then we identify the redundant joint forces as well as the joint forces which are corresponding to the unrestrained degrees of freedom, which means that we are not only interested to know the restraint or the redundant forces, but we are also interested now to know the forces which are corresponding to the joint which are free to take place. We will briefly see that what is the intention of doing this. Then we convert these overall system into a equivalent joint load system also, so that all the forces are now active at the respective joints of the given problem, and then we try to evaluate the standard unassembled flexibility matrix of the given system, the action transformation matrix or the BMS matrix which we typically describe in the given system, and also we define the structural flexibility matrix and the other output parameters of the given system. And once we have done all these given values, we will just try to do a small post processing where we will try to include those number of external load components which have not been added in the actual calculation up to the initial steps of the given problem, to calculate the final values of the support reactions or the internal member forces. Now, to start with the member process, we first define the degree of static indeterminacy. As we have already seen that it will remain same. We have 1 degree of static indeterminacy on the given problem. We can again consider that this amount of the reaction has been considered as a redundant of the given system, whereas the given system now will also be considered with respect to the free degrees of freedom in the given problem. So, we consider that at the joint A, at the joint B and at the joint C, the rotations are free to take place, which makes us to say that in the given problem now, other than the A of r, we also have 3 joint forces which are corresponding to the joint force 1 with respect to the theta A being placed in the given problem, joint force AJ2 which is corresponding to the direction of the theta B in the given system, and joint force AJ3 which is corresponding to the direction of the theta C. Together constituting these all parameters of the given system, we call that this is the overall structural load vector of the given system. So, in a given system we consider that all the external loads which are active on the given problem, either as a redundant or at the degrees of freedom which are free to take place, they constitute the overall response of the structural forces. And if I now able to convert the given system into a equivalent joint load of the given system, the statically determinate system which is considering the A of r as a redundant will undergo any kind of a deformation only due to these structural load systems of the given problem. So, to see this part in a very systematic manner, we consider that the given system has been converted into a equivalent load system. So, now this is the equivalent joint load system which is identified. Now, as we defined in the previous step, the overall system has been considered as the system subjected to the 2 joint forces, and this reaction of the given system has been considered as a redundant value of the given system. So, this has been included as a of r or the redundant value of the given system, and at the same time the system is now not considered with the member forces, but rather it has a joint forces which are active in the manner of this in the given system. So, now what we understand that for this given system, any kind of a deformation which is taking place in the given problem is only taking place due to the loads which are active in the direction of the joint forces, the third one being the rotation over here, or the A of r which is available at this given system, because all the other remaining degrees of freedom are restrained for the given problem. Of course, there is a WL force which is also active here with respect to a partially restrained system, but if I just consider it to be restrained, fully restrained at one condition, I can simply say that the given deformations which are active in the given problem are only due to the conditions of the restraints or the joint forces which are active as the A of S components in the given system. So, we understand A of S is a contribution which has two parts, the redundant system and the joint load system in the given problem. Now, the joint load system, if we typically describe, is the contribution which is in the direction of the three unknown displacements of the given system, which are the rotations 1, 2 and 3 of the given problem. So, I can evaluate these three components as the first one being WL square upon 12. The positive sign convention gives me the value in the anti-clockwise direction. So, I will write it as minus of WL square upon 12. The second one, which is rotation with respect to theta b, and I consider that the direction of the moment here is also in the same direction. So, it comes out as WL square upon 12 for the given problem. Then finally, the theta c, which is rotation at the point C, but corresponding to that we do not have any force or any active moment there. So, I will consider that this A of j component is 0 in the given problem. So, these are the three values of A of j 1, A of j 2 and A of j 3 in the given problem. What we have not added at the same point is the contributions of these reactions which are active in the direction of those supports which are restrained in the given problem. We can just keep them in a separated manner and we can call it as A of R 1, and they again appear as WL upon 2, which is corresponding to the reaction at the joint 1. Then similarly, WL upon 2, which is appearing as the reaction in the direction of the joint B of the given system, and these values are downward. So, we will just consider them with the negative sign, so that they are considered with respect to the positive sign convention which is upward positive in the given problem. Now, the idea is that these components will be added at the end of the given process, because while doing the analysis we are not adding these components in the analysis procedure of the given system. So, as we move ahead with the respective terms, we consider now that as a step 4 we want to evaluate now the member flexibility coefficients. So, to include the member flexibility, we will break the overall system into the member components. So, this is the member 1, this is the member 2 and this is the member 3 of the given system. For all these three members, we have considered the set of forces, the member forces which could be active, while the member 1 and 2 happens to be the beam member. So, there are two set of forces similar to the translation and the rotation of the given system. Corresponding to that, the vertical shear and the moment of the given system have been released, but the member 3 happens to be a spring system which can only have the axial forces, and that is defined with the AM5 component of the given system. Now, we know that for the regular these kind of a system, the generalized flexibility matrix is known to us. So, I can define the value of f of m1, which is the flexibility matrix for member 1, f of m2, which is the flexibility matrix for the member 2, f of m3, which is the flexibility matrix for the member 3. While f of m1 and f of m2 will be a 2 cross 2 matrices for the given system, f of m3 will be a matrix which is only containing one component, because it is corresponding to the axial deformation of the given member. And that brings us to say that f of m, the unassembled flexibility matrix, is a 5 cross 5 matrix of the given system. By knowing these parameters, we can now move ahead and identify the action transformation matrix of the given system. As the procedure says that the overall system, which is broken into these three sub members, is initially defined with respect to this kind of a condition, in which we have considered this member as a redundant part, whereas there are three joint components of the forces which have been defined in the given system. So, now what we will try to do, we will try to evaluate the respective values of AM1 to AM5 while we release the individual values of AR1, AJ1, AJ2 and AJ3 in the given system. So, the idea is that as the deformation of the given system is primarily contributed by the redundant value which is unknown for the given system, and the forces which are active in the direction of the joints which are free to take place, with respect to all these set of forces or the structural force system, we will try to calculate that what are the contributions of the member forces, and that connects us to say that the A of m can be described, which is containing all the 5 values A m 1 to A m 5 in terms of the A of s or the structural load system of the given problem, and that is connected by the B of m s or the action transformation matrix of the given system. So, to evaluate it, we come up with a simplistic procedure. We define the structural system which is having all these 4 number of components which are defined, and then we have the member system in which we have all these 5 number of components identified, and now we understand that one by one we release each of these structural components and calculate the member forces corresponding to that. To do so, we will be evaluating first the A of r which is released in the given problem, say with the unit value, and calculate all the forces in the given system A of m 1 to A of m 5 in the given system. This gives us the value of BMS or the action transformation matrix in the given system. In the same manner, we can also evaluate the reactions of the given system. So, we have identified that there are 2 reactions R1 and R2 in the overall structural system of the problem. So, with respect to release of each of these components of the action structural action forces, we will also evaluate the reaction R1 and R2, and that is connected by B of Rs matrix of the given system. So, the action transformation matrix and the reaction transformation matrix typically connects the amount of the member forces and the reactions of the given system with respect to the structural forces which have been identified in the given problem. So, I think this procedure of individually identifying each of these components we are not again showing, but if you will just do the free body diagram for all these determinate systems, you can evaluate these values. So, typically any of the column refers to the value with respect to say A of R1, this is with respect to A of J1, A of J2, A of J3, and the individual column values refer to the values of A of M1, A of M2, A of M3, A of M4 and A of M5 in the given system. So, with respect to each of these values, once we release the given system, we evaluate the member forces by the simple free body diagrams. Once we have evaluated these action transformation and the reaction transformation matrices, we can evaluate the overall structural stiffness or the structural flexibility of the given system by doing the matrix triple product. So, BMS transpose F of m, which is the unassembled flexibility matrix, into B of MS. This gives us the overall structural flexibility matrix of the given system. And as we realize that structural flexibility matrix will be containing with respect to the 4 number of terms which are available in the structural system A of S, which contains A of R and A of J, 1 value of the A of R and 3 values of the A of J in the given system, and that is why the flexibility matrix for the structural system comes out as a 4 cross 4. We have done this calculation in a computing platform, but if you want to do it at the same point, you can use either the MATLAB or you can also do it using the simple manual procedure. Once we have evaluated the flexibility matrix, we go to the evaluation of the response of the given system. We consider that the evaluation of the system response can be done in the same manner, that the system response delta of R and delta of F, which is corresponding to the free degrees of freedom in the given system, or we call it as delta corresponding to the joints which are free to take place, is defined by the amount of the flexibility matrix, which is F of RR, F of RJ, F of JR and F of JJ in the given system, multiplied with A of R into A of J in the given problem. Now, what we understand, at the given system at any point we have the F of RR, which is corresponding to the restraint system. So, this will only have one coefficient. F of RJ is connecting the restraint value with respect to the joint deformation systems or the joint forces of the given system. So, it will have 1 row and 3 columns in the given system. So, this will have a size of 1 cross 3. Similarly, F of JR in the given problem will contribute the component of the delta j, which are having 3 values, and it will be including the corresponding system with respect to the A of R, which is the single force value in the direction of the redundant. So, this will have 3 number of rows and 1 number of column in the given system. And finally, f of jj, which is having the 3 number of values corresponding to the given joint displacements, which are defined in terms of the 3 number of forces in the direction of these joint deformations, and that will be having a size of 3 cross 3. So, the overall f of s which has been evaluated can be broken into these kind of sub matrices, which will give us the individual values of the f of r. So, we can describe it in this manner, that this is f of r r, this is f of r j, this is f of j r, and this overall matrix 3 cross 3 is f of j j in the given problem. So, once we have all these values available to us, we can simplify the equations for the unknown parameters of the given system. What we realize, the delta of r is a one parameter which is known to us based upon the compatibility condition. Delta of j is the unknown parameter, so we need to evaluate it. A of j in the given problem is also known to us, because these are the joint forces which are active in the degrees of freedom which are free to take place, and A of r is the unknown redundant value which we want to evaluate. So, out of these equation, we have now having 2 values known to us and 2 of the values which are unknown to us. So, by writing 2 set of equilibrium equations, we can evaluate the given system. Now, in order to calculate the value of delta r, what we realize, that while all the forces have been considered while writing the given set of equations, we have not considered the contribution of the spring in the given problem. And now, the spring contribution will be considered with respect to the load which is active directly at that point. Now, over here one must note very clearly that in order to calculate the delta r value, now we have not evaluated the component of the A of r in the given problem, because A of r has already been included in the given problem by considering the contribution of the flexibility system which has been contributed. So, we will be writing the given system with respect to the individual parameter of the load which is active at that position, and that is the load of W L only. So, that is why we consider the delta r, which is corresponding to the W L which is acting in the downward direction, and corresponding to that multiplying it with the amount of the flexibility matrix of the given system. And once we solve this given problem, we get the A of r, the unknown redundant value of the given system. Now, this redundant value is not the final value, we need to further modify it with respect to the external load system. So, now what we do, we evaluate the reactions of the given system R 1 and R 2, which are also calculated with respect to the reaction transformation matrix into A of s, which are the structural system. So, these are the initial reaction support reaction values. We also evaluate the initial member forces which also appear with respect to the action transformation matrix into A of s in the given system. Now, as we already said that these are not the final values, we need to modify them with respect to those forces which have not been added in the given process up to now, and to do so we realize that this is the given system which was initially identified. In the reaction system which was evaluating the values of R 1 and R 2, we have not added up to now the system of W L by 2 and W L by 2 which are active in the direction of both the reactions. So, we add this part in the given process. As these loads are downward, so the component will be added in the given system which is in the positive manner. One can also add this component with respect to minus of A of R 1 which we did earlier in the given process, or 1 of A of R L in the given process which we have identified, and this will give us the final value of the support reactions which will be available in the given problem. In the same manner, one can also define the A of R final, which is the redundant value, A of R which we have already evaluated in the previous step, and the W L component, the load amount which has not been added in the previous step of the given system. So, we add that component as well, and that gives us the net value of the redundant value at the given support C of the given problem. And finally, we have the member forces of the given system. What we realize that for member forces, we have to add the member force component with respect to the fixed ended system as well. So, we evaluate the fixed ended system. So, over here also there will be the member forces which will be contributed, and we evaluate their contribution as the A of M 1 which is equal to W L upon 2, A of M 2 which is minus of W L square upon 12 because of the first member. Similarly, when we move to this point, the second joint over here, we realize that A of M 3 will be the value which is 0, because there is no load which is active on this span of the given system. So, any of these load which are active on the span of the system will only contribute to the AMF component of the given system, which is the fixed ended reactions of the given system due to the member loads. Now, similarly AM4 will also be 0, because in this given member span BC there is no external member load active. And finally, when it comes to the reaction of the given spring component, so with respect to the AM5, we realize that this value will be minus of WL, because the load is active downward. So, we will consider that this contribution is minus of WL in the given problem. So, we add this component in the earlier obtained value of the A of M, and that will give us the total final value of the member forces in the given system. So, once we are done with this whole process, we realize that the overall response of the system can be evaluated. As we have already covered a few more problems earlier in the sessions, we briefly discussed this part of the problem. We did not spend too much time to evaluate each individual coefficient of the given problem, but it is believed now that with the all set of discussions which we have done in the previous set of lectures, one can easily go through this content and try to see it, and one can evaluate the response of the given system with the set of values which we have defined in the given session. With this, we stop over here. Thank you everyone.